to this session about Apache Kafka for mission-critical deployments of machine learning and models. So that's the topic I want to talk about today, and that's a huge topic. We see a lot of different customers. So they often build cool models, and then they are not able to deploy that in production and really at scale, and whatever scale means. So that's also the first thing I want to talk about in the beginning now. So what is extreme scale? That was a little bit the title and the motivation of the talk, but it can be different things. Many people first think about very high volume of messages, like millions or billions, or very big data sets. But that's not always the part. Often it's more like dynamic scalability. For example, if you want to train some models with TPUs or GPUs, you just need it for some hours maybe. And also sometimes mission-critical deployments at scale, that means really for doing the predictions in real time and very fast, in a scalable way that you can scale the instances to hundreds or thousands of predictions per second. And then often it's also about hybrid deployments where you run it in different instances, like different clouds or on-premise and so. So whatever you mean with extreme scale, it's different points, and at machine learning, that's all important. It's not just about training a model at scale with GPUs or so in a cloud, but really about the complete ecosystem about that. That's really the important thing first. And so now for the agenda, what I want to show today, including a short live demo at the end, is really shortly talk about what is machine learning in the end. Everybody knows probably really the motivation for this talk, why bring it in production, and really in a mission-critical way to add business value. And then I will focus on the Kafka ecosystem and why so many people use it in different parts of their machine learning environment. And there I go into more detail about things like data ingestion and data pre-processing, and then also the deployment of the model and how to automate all these things. So this focus is really about how to bring machine learning to mission-critical deployments in production. That's the main goal, because that's what we see many, many companies have challenges with. And that's where then often Kafka comes into play, at least for some parts. So let's begin with the motivation. So why do people want to use machine learning in their processes? So the main definition first, so machine learning or then also deep learning is used to find hidden insights without being explicitly programmed. I think that's really the key point. You don't write Java code and write if, else and some for loops and so on. You don't write typical applications, but it's really learning based on big unstructured data sets to get new insights of that. That's in the end what we use as predictions for the future. That's the main goal, and with that we have then many different algorithms and concepts and implementations of that. So there is decision trees, clustering. As one part, there's also neural networks, which is the buzzword deep learning behind that. But all of these are very important. So for different use cases, you use different algorithms and different models, and therefore also different frameworks. It's not that TensorFlow is the only framework good for everything, right? For some things like deep learning, it's great, but for some other ones, there are much better frameworks. So it's not the one option you can choose for that. But in the end, remember really that no matter which one you use, you learn and learn, so the computer learns, and by that it finds new insights to make predictions on future events. That's the main idea of machine learning. And there's a lot of real-world examples, and everybody of you uses that. There are things which is out there for many years already, like spam detection in your email folder. If you think about that, you cannot program that explicitly. If you think every email and every spam email, it is different, and it changes all the time. You cannot write that with if-else loops for all the billions and billions of emails and spam emails. So a model has to be built which learns that. So it can predict if an email is spam with a specific probability or not. Right? That's the idea behind machine learning. Continuously learn and train a model to make predictions with a specific probability. And this was improved more and more. So for example, if you do use a search engine then you do get search results, but you also get a lot of product recommendations. In the end, the advertisement, how Google and the other companies make billions of dollars, right? Under the hood, it is no if-else programming explicitly. It is learning for every specific person, context specific, so that everybody in this room gets different recommendations. Because with this, leveraging machine learning under the hood, the tech giants make much more money because they give you specific results. And this improved in the last years more and more, and that's also where deep learning is coming into space for new use cases, like image or video recognition. So for example, if you upload a picture to Facebook, it analyzes the picture. It detects you, it detects your friends, it even detects the location where you are. Even if you don't have a GPS on, right? It detects the location based on the picture. And with that again, Facebook can make better recommendation, better analysis of all the data you and your friends sent there, and with that they make more and more money. And then this is getting more and more autonomous. So for example, I think 2 years ago or so, there was AlphaGo, which was announced by Google beating the most professional Go player. Go is a game much more complex than chess, and there they built a model to beat the professional players with that. In the meantime, they stopped these projects because the models were too good. They bet every player on the planet. Right? This is just one example, and this is so improving more and more from the spam detection, the more or less simple use case, where you might also use it with some other patterns. And now it's going to things like image and picture and video analysis and very powerful things you can do here. And now the goal is that more and more companies want to do that, because the examples we see here, that's famous stories from the tech giants, right? But in the meantime, every industry can leverage machine learning. You can leverage it in banks and telcos and retailers everywhere. So here are also a few examples for that. And the funny thing is that's the common use cases you already know and implement in your company. But machine learning does not really change the processes behind that, but they improve the processes. So for example, if you think about make real-time decisions, for example, fraud detection. If you have a few seconds to decide if something is fraud or not, you can either use the existing algorithms or you can leverage machine learning, which gets better and better with more data you feed into this model. Or think like cross-selling with Internet of Things and mobile devices. While you are walking through the store or through the airport or through any other public building in the future, you will get recommendations if you allow it on your smartphone, and then you get that based on analytic models so that everyone gets a specific advertisement or coupon or whatever, context specific for the right time, right person, right context. But this is also for longer things, like minutes, like in transportation rerouting, in logistics, for example, if you want to avoid traffic jams, for example, or if you're in customer service, if you're on the hotline with your service, and then they get recommendations based on the model. So depending on what input you give, you get better other recommendations or a better coupon or whatever your problem or use case is. And then there are things which is longer term. Like one famous machine learning scenario is predictive maintenance, which we hear everywhere, like automobile or manufacturing companies. And there it's really more about hours or even days, where you analyze sensors and then you do predictions on that. So if first you feed in multi-million of sensor events and analyze them to build models, and then based on that, you analyze future events to make predictions if a machine will break in the future, or if you have to replace a part at the best time to save most costs and to optimize your business process. So this is processes everybody has in its industry, and now you can improve them with machine learning. And the key problem is really not just to build a model which does this, which improves this by detecting the fraud, or by doing better cross-selling, or by predicting if a machine breaks, but by bringing all that into production. And that's where we come to scale. Whatever scale means, it can be the model training, it can be the deployment of the model, it can be the monitoring. All of that is really many, many events, and it has to scale up and down and really be mission critical for 24/7 deployments in many scenarios. And that's in the end what I want to talk about today. So also important, there is not the one single all-rounder machine learning framework. So in the companies I work with, we see many different technologies and frameworks used. Like many use things like R or Python as programming language, or any kind of tooling like RapidMiner or maybe SAS analytics or so. And then you have frameworks behind that, like Apache Spark, or like deep learning specific frameworks like TensorFlow or Deep Learning for J. We also have a few standards like PMML or ON and X. Sometimes they are good, often they are not that good because they create more trouble than they help. But in the end, you see there is a lot of different options you have to build machine learning. And so the key thing here really is there is no all-rounder. And for your specific projects and infrastructure for machine learning, you typically build an independent architecture, which you then can use to build different models with different technologies and deploy them also in different scenarios, maybe even on mobile devices or somewhere at the edge in Internet of Things environments. So that's more or less the situation. And what's also very important, the other part, there's a lot of hidden technical depths in machine learning systems. So you really have to think about the mission-critical infrastructure at a complete thing. So not just building one model with Python and then, okay, give it away to the engineer and he has to deploy it somehow, because that often fails, and that's exactly what we have seen in many companies. Because if you take a look at this small thing in the middle and in the back, you can't even read that. Only this small black box is really writing the source code, which you do in Python, right? That's a small part often. That's 10 lines of code, maybe 20, maybe 100 or so. It doesn't matter, but it's not really the big infrastructure where you have all the different processes of a machine learning infrastructure and process, like data ingestion at scale, like doing validation of the model, like serving the model when you deploy it in real time for processing. And then also, of course, things like monitoring all these things, and then improving the model, redeployment, A/B testing, which model is the better one. All of that with many different technologies and models under the hood. So you see here, writing the code for the model is just a small part of the story, when you really want to build that for mission-critical deployments. And with that now, we come to the motivation, why so many companies use Kafka at some part for machine learning infrastructure. So not everything is built with Kafka, but you can do a lot with that, and that's in the end what I want to show you today. And seriously, most companies use Kafka at least for some parts when you think about machine learning in production at scale. So let's start with the general thing. So what is Apache Kafka? It's just 2 intro slides so that everybody has the same knowledge. I hope most people know Kafka already. But in the end, Kafka is a distributed commit log. It was built for very high volume processing and for high scalability. So you can use it for a large scale, but you don't have to. You can also use it for lower volumes. You can use it for both. That's the good thing, and that's what it is used for. It's not always about terabytes and petabytes, but sometimes it's also about smaller events. And with that, as a messaging and distributed storage layer in the middle, you can build an infrastructure for machine learning. And that's actually how many of the companies do it. So not just the tech giants, but also the traditional companies like the banks and telcos and so on. Under the hood, Kafka is a messaging and a storage and a processing system. So it's much, much more than just data ingestion into Hadoop, which it maybe was 8 years ago when it was founded at LinkedIn. So that's in the end also what I will talk about today, what you can do with Kafka and its open source ecosystem. First of all, if you have never heard about Kafka, seen it a lot, you don't have to worry about really, is this the right tool for using it at large scale? So there's plenty of examples on the web, not just from tech giants, but also from other ones. But here just 2 examples. So LinkedIn, and this is numbers from 2018, LinkedIn sends over 4.5 trillion messages per day via Kafka. So 4.5 trillion messages per day. That really scales well, right? It's much better than most other traditional messaging systems, and so you don't have to worry about that. And also, if you think about the size of data, Netflix processes up to 6 petabyte per day of messages, right? Per day messages, which are used by Netflix, which go through Kafka pipelines. For all the different components. It's not just for data ingestion, but also for processing, monitoring, transformations, all these things you have to do in a machine learning pipeline. The important thing is we have to do a lot here, and it's not always at that scale, right? That's the thing that you see, it can do it in that scale, but it's also the same benefits for much, much smaller scale. So here's 2 examples. The first is Netflix Meson. This is an automation engine they have built for machine learning pipelines based on Kafka. So all their pipelines are going through Kafka for that, and with that they build different analytic models with different frameworks. It's not always the same depending on the use case. Here is one example where you can also read a lot behind that link under the picture. For example, here they do recommendations for the user, where you can learn, where they learn which next movies to recommend you. And that in the end, you see that in real time in your app, on your mobile device, wherever. And that's of course different for every user, so it really also has to scale, not just for training the model, but also for then using it later for deployment, for inference. On the other side, the next example is Uber. As I said, you can Google for any kind of tech giant. They all use Kafka here for machine learning pipelines. eBay or PayPal, you can search for everyone. Probably you'll find something about Kafka here. And they also built their own platform for ML, and it's really important. It's an end-to-end workflow system. It's not just data ingestion, it's really the whole system around machine learning built with Kafka and some other technologies, and they also support various AI technologies. So it's not just only TensorFlow, so it's many different ones depending on the use case you have, on the problem you have to solve, and which one works best for you. And sometimes different are combined to work best. So this is 2 examples of how 2 of the tech giants do it, and now let's think in detail about how can you do that, or how do our customers do that, and many others on the public web where you can read about that. So Kafka, as we said, it's messaging plus storage plus processing. So you can do a lot with Kafka under the hood. And so here you see, you typically have things like data ingestion. That's the first part. You need to gather a lot of data to build your models. That's where you have your feature data input into Kafka. You can store it there, you can send it to other systems, you can process it there. And then you build your model, which you see here on the right side, with any technology like TensorFlow or H2O, whatever. And then you deploy your model to the here left side into production, where it again has to scale. And scale in terms of performance, that it maybe has to execute in a few milliseconds or so, or maybe scale in volume, that you have to really even do the predictions for hundreds of thousands of events. And that's more or less the high-level overview of Kafka in the middle for doing all these kind of things. And also the important thing is that the Apache Kafka open source ecosystem is much, much bigger than just Apache Kafka. So even just Apache Kafka has already Kafka Connect, as you see at the top, which can be used for integration of different systems. And then you can use Kafka Streams for doing stream processing. I will talk about that in more detail. And you have different other Confluent open source components. They are also all about under Apache 2.0 license. For example, you have different clients if you don't want to use Java as language, but really directly use Python or Go, for example. Or you can use things like KSQL for doing SQL analytics instead of writing Java code. So simply there is a whole ecosystem which many companies use to build their machine learning infrastructure. The key here is that with this you have the advantages of the scalability and flexibility, but also you're independent of one technology. And that's both for the provider side, so you sometimes don't want to go to just one provider on premise or in the cloud, and also for the machine learning technologies where you have to use difference in this infrastructure. So this talk really is more or less about the Kafka infrastructure part, the machine learning infrastructure. It's not so much about many other challenges the data scientist has. So the data scientist itself typically spends 80% of his work time for doing things like data analysis, data preparation, data pre-processing, and not just writing the model. As I said before, writing the model, that's 20 lines of code. That's not that big problem. It's, of course, easier than in the real world, it's more complex, but it's not that big part of the whole thing. And therefore, you can also even use things like AutoML, which is one of these new hype things, where vendors like DataRobot or all the cloud providers offer you a service where you just upload your data in CSV files or in another format, and then they do all the things you see in this left box on the left here, like pre-processing, like finding the right features, building different models, do A/B testing. So that's more or less a black box implemented by many different vendors, where you just upload your data all the time, and they build the models for you, and even they give you the best model out at the end. And that's things, as I said, like DataRobot or the Google, Amazons of this world, they all have these AutoML technologies. So that's a different story, and it doesn't work for every use case, and often the data scientist can do better results, but that's the data scientist job. That's not the focus of this part. The part of this talk is really to, no matter who builds the model, the AutoML tool or the data scientist, to bring that into production later. So both for the training the model, the ingestion, and also then for the deployment and monitoring and so on. So the first great thing about Kafka here in the middle is, so typically, no matter if you use AutoML or data scientist, you build different models from the same data, and then you compare them to each other, and you find out which one is the better one for things like A/B testing, to try out different models. And as Kafka is not just a messaging system in the middle with large scale, but also a storage system where you can store your data as long as you want. It's just a distributed commit log, so every message is appended to the other one, and so you can reread the messages again and again and build different analytic models with the same data. That makes them better comparable, and that's very efficient with Kafka, but still scalable. And like you see in this example here, you can build, for example, 2 different TensorFlow models, and then maybe use another technology, like a DataRobot, which automatically builds another one to compare it to this one. You can use all of that on the same data set, because Kafka is built as event stream, but it's also distributed storage under the hood. And that's a huge advantage why so many people use it for machine learning also. So that was the main motivation, so why Apache Kafka ecosystem as infrastructure for machine learning. Because it's not just a messaging, but also storage. You can also process data, and it simply scales well. And it's independent of all the technologies and all the providers like the cloud or on-premise which you use. With that, let's think a little bit more about the detail. And here again, you see in the agenda, this talk is not about building the model, because building the model itself, that's done by the machine learning framework like TensorFlow, right? That happens after you get the data in via data ingestion and pre-processing, and then you build the model for an hour, or for a day, for a week, depending on the complexity. And then you get a model output, and then you deploy that again somewhere. And that's again where we talk about. And then also you have to monitor and automate all of that. So the combination of Kafka with all these machine learning concepts of the frameworks, this makes it so powerful. So let's now think about the different steps you have to do it. On the left side, you see again the whole picture of all the different components which you have to do for a machine learning process, training, building, testing, monitoring the model. And so the first part is, of course, you need a pipeline to ingest the data. For machine learning, you typically need bigger data sets, because otherwise you cannot learn well. So it doesn't make sense if you have just 100 or 1,000 records. Typically you have hundreds of thousands or millions of records, depending on the use case, to train a model to really make good predictions for the future on new events. And for that, you need to ingest the data. In 90% of use cases, people use here Kafka anyway, because it's really working well, it's vendor independent, it's open source, and you can simply scale it well. And so no matter where you ingest your data to, like in the cloud or maybe somewhere on-premise with something like Mesos or somewhere else on-premise, it doesn't matter what, you have the huge advantage, of course, with the cloud that you have extreme scale, because you can just send it there and then scale it up and maybe delete it later when you don't need it anymore. And also you can leverage the special hardware like the GPUs or TPUs, which you can only have in the cloud often. So you ingest the data, but that's also the first problem. Besides the general problem of having the scale for ingestion, how do you integrate with that data? And that's where many people also use Kafka Connect on both sides. On the one side for getting input data, like from sensors, from feeds, from things like MQTT or other sensor events, or maybe it's just social feeds from Twitter. And you ingest all the data, and then also after you have to, in Kafka, you want to store it somewhere for analysis afterwards. This can be Hadoop with HDFS, this can be a cloud store like Google BigQuery or S3. This can be anything, and there then you build your model on top of that with the specific tool you want to use. And for this combination then, for data ingestion and integration, Kafka is used as ingestion layer with large scale. And based off that, you can use Kafka Connect, which is a framework as part of the Kafka project, which offers connectors and large scalability. Because under the hood, it also uses Kafka for that. And with that, you can build a very powerful and flexible infrastructure for integrating with different systems on both sides for data ingestion to the machine learning endpoint. So after that, the next step is then data processing. And for data processing, yes, you can use just things like Python or R to do some hand coding and do some analysis. And that's often fine in the beginning when you want to analyze what data is important. That's where the data scientist often spends 80% of his time to find the right attributes and features, to prepare them the right way. That's good. You don't have to do that at large scale. But then when you think about bringing that into production for really training terabytes of data from the sensors, and then also later for serving the model, here you need the feeds of data which scale well, and here then the people use Kafka for that. And the benefit if you use here Kafka in the middle, and the data processing also with Kafka technologies like Kafka Streams or KSQL on top of that, you also have to implement that once and can use it for both parts. For the ingestion part, for pre-processing, and then also for the same pre-processing which you need again when you want to do the prediction on the deployed model. Because you typically have to implement it twice otherwise. You have to implement it in the Python part for analysis, and then later in the real-time production thing where you have to scale it. Because things like Python don't scale on that level. So another component which we often see is the Confluent Schema Registry. It's another open source component, which is also used especially if you have different inputs and outputs. Because with Kafka you can process many, many messages, but often these messages change over time. There's an evolution of the schema of the messages. And to have a validation here and ensure that only the right messages get into the right place, at many different parts, like at the data ingestion part, or when you predict the events in real time, you want to validate the data, and therefore we see more and more deployments where the schema registry is used for validation. It's also running more or less on top of Kafka, so there is no external database or so. It simply is another Kafka topic, and it validates then under the hood the different incoming and outgoing messages. So this was data ingestion and pre-processing, and I know it's only 40 minutes, so it's pretty high level what I talk about. This is really just to give you the overview about what many people do and companies do in real world, and you can read a lot of blog posts about more detail about how they leverage that there for data ingestion and pre-processing. As I said, especially for the data ingestion part, you can read from any tech giant about how they do that. Let's now also think about the other part of the story, because building a model is one part. And that's the first story, but then you want to deploy that to production. And that's often also where the challenge is between the data scientist on the one side, which use Python or R or SAS to build a model, and then the other side where the Java developer has to bring that into production. Production means 24/7 with no downtime, with good performance and all these things, scale it up to different services that you maybe in the beginning only process 100 messages per second, but later maybe 1,000 or even more. And therefore you have to deploy it somewhere. And this is again where we see more and more people using Kafka Streams for that, because Kafka Streams is a stream processing engine which leverages Kafka under the hood. So what do we mean with that? So really the point is we want to deploy our models somewhere in an application, and for that we need to use stream processing in a what I called extreme scale in the beginning, where it really meant where you do real-time continuous processing of data. If you have use cases like Internet of Things or cross-selling or fraud detection, you want to continuously process the data instead of storing it in a database and then processing it a day later, or even an hour later, because then the fraud already happened, or the customer already left the store, or the machine already broke. So you have to continuously process the events, and now you can also leverage machine learning models here inside. So this is also the flow you see here. You have input data, then you process it via Kafka with Kafka Streams or KSQL, and then you send the output prediction somewhere. So the key difference really is that for extreme scale, you need to do real stream processing. That means that you process data while it is in motion. So before storing it into a database and request response, that's not working well, and that's not the right process. Every modern company or project does stream processing where it continues to process data. That's things where you can also use things like Spark streaming or Apache Flink or Heron or Storm or whatever. Or based on Kafka, you can also use Kafka Streams here. The point is really to process data while it is in motion. From Kafka perspective, with the open source ecosystem, you have different options to do that. You can use an API like Java or .NET or Python, where you just write your own Kafka consumers and producers. And then we have Kafka Streams, which is the stream processing library of Kafka, which you can use for that with Java code. Or you can use KSQL, where you just write SQL-like queries and deploy them in production. Right? That's the three options you have. All of them are based on Kafka. The huge advantage of them, and that's why so many use it more and more, is that in contrary to all the other big data stream processing systems, it's not a big data cluster what you have to run. It's just a small, lightweight application and library which you can run anywhere. So as you see here, you can, if you're not that cool in your project, you can deploy it in a WAR file, in a Java EE application, or maybe you already use things like Docker or Mesos or Kubernetes or whatever. It doesn't matter, it's just a small Java application which you can deploy everywhere. And a huge advantage of that, and that's especially also relevant for machine learning projects, you want to focus on your business problem and your business application and leverage machine learning there. Like fraud detection, cross-selling, predictive maintenance, or whatever. But you don't care about all the other departments and projects and their problems. You don't want to run everything of that in one big data cluster. And therefore, you build your small, lightweight microservice or application with leveraging Kafka Streams or KSQL under the hood. That's more or less also the key difference compared to the other solutions like Flink or Spark streaming, which also have their advantages, of course. It's always trade-offs. But here, the key advantage is that you can have loosely coupled, lightweight, but still scalable microservices based on Kafka. And the other side is, as you use Kafka anyway for data ingestion, and 90% of people do that, why not use Kafka Streams for some of these parts if it's the better fit? Because the important thing is Kafka Streams and also KSQL, both open source, but they are built for scale and for mission criticality. So we have many customers which run that 24/7 at large scale, and that has to run all the time without downtime. And that's what it is built for. You can develop it on your laptop in a small Java process, as I will show you in the live demo in a minute, and then you can scale it up and scale it up more and more. Right? So for example, if you're a retailer, and let's say you have 10 Kafka Streams microservices running in parallel and processing all your events, and for every event you do a prediction with machine learning, and then before Christmas it goes up to 100 because you sell so much more. Then you can scale the Streams microservices up. You just start 90 new Docker containers, process all the incoming events in real time, and after Christmas you stop them again and you go back to 10. So this dynamic scalability and flexibility is built into Kafka Streams because it's not a big data cluster like Spark or Flink, but it's just a small library you run anywhere, like on Kubernetes or in the cloud or where you are. So let's take a look at a small demo here. The demo part is now really about the deploying a model to production part and not about the data ingestion and pre-processing, which is done before, of course. But due to time constraints, I have to limit all of that a little bit. The story here is that it's about airlines and about flight delay predictions. That's a big business case. Everybody tries to get the best results here all the time already, but if you are flying a lot like me, you know that both the airlines and the airports have a lot of problems predicting delays. So often you already sit in a plane and then you get information, okay, we have still 21 minutes delay. And if you think about all the logistics and cost and also the customer satisfaction and all these things, you can get so much out of that if you can get better predictions for your flight delays in real time, or even if it's near real time, right? And I have built here a small, more or less demo model with H2O and TensorFlow in this case, where I predict flight delays based on incoming data. And the output data can then be sent anywhere, to an alerting system, to a real-time monitoring UI, using a short message text to the customer mobile smartphone, whatever, right? So it's a great use case as an example. So let's take a look how that is implemented. As I said, in this case, I have already built a model. So the model was trained and built, and in the end, it was also exported. So I hope you can also see it in the back a little bit, but the point here really is not the details, not the source code. And the main idea is important. What you see here is, this is the model first. This is an analytic model built with H2O. It was generated, so I didn't write this Java code. It was generated by H2O. And that's also one of the reasons why I like H2O a lot. It's an open source framework which generates Java code. So this, as you can assume, scales very well. So you just embed this Java class into your application, in my case a Kafka Streams application, and can then run that. So this model performs in, I don't know, 10 microseconds or so. So much less than a millisecond, right? So it's really built for real time. But I have also built other examples with TensorFlow, so the technology doesn't matter. The point is you have this model, in this case H2O, and I create a new Java object out of that. This is now my Kafka Streams application. My Kafka Streams application is one class, a public static void main method, so it's really one class which starts up as Java process, and I just embedded two things. I embedded the analytic model, which was the other Java class, and the Kafka Streams library. It's also a jar. That's the two jars I have in this application, and that's it. So you can already assume that it's very, very lightweight, right? So that's a few megabytes or so. And you can run that everywhere, in a Java EE application, in a Docker container, whatever, depending on how you want to start it. And then the business logic is also not that much. I just map the incoming data, which is in this case airline input information, to my object from my H2O model. Right? And in this case here you see in the middle, P is model.predict binomial. That's my one row which does the prediction. Right? This is the row. Here I leverage the analytic model which I've built before with H2O and TensorFlow. And this model is then applied here to do the inference on the incoming flight data which you see on top of that, which I map into the object. And that's it. That's one line of code where I apply the model. And then after that, I have to do something with the prediction. And in this case, as you see here, I do a prediction and send it to an output topic. So the incoming feeds are coming in real time to the input topic to Kafka. And then this is just this one class which does a prediction in this case by applying an analytic model. And this scales so well. This is execution is a few milliseconds of the whole process. And the model itself takes a few microseconds. So let's take a look if that really works. Here I have already started on my console a Kafka console consumer. This is waiting on the output topic. So this is waiting for predictions. So for every incoming new thing, it will do predictions. Now I start my Java application. As you see, this is really a public static void main. It has two dependencies, the model, which is in this case a Java class, and the Kafka Streams jar. That's all it is. And that's how you can deploy it into Docker, Kubernetes, in the cloud, or whatever. And that's also what you can then scale up to 10 instances, to 100 instances, to 1,000 instances. It scales automatically, including failover and all these things, because that's built on Kafka, which has these features. And it scales well. So what I'm now doing, I have started the Java application. It's waiting for doing the processing under the hood. And now I'm creating new test data. This is really just hello world, so I do it one line by one line so that you can see the output well. And here the input is now test data from one line of test data with one flight information, right? This is, for example, the starting airport, the arrival airport, the departure time, and a few other characteristics which are features which are used by this model under the hood to train the model. And of course, for the pre-processing part, the input to this topic has to be the same data now. And that's what I do. And so you see here now, I will send one message to my Kafka input topic now, as you will see here, and then we will see as soon as I click on return, it will also show the output on top. So on top you see already the prediction. So you can't even measure that with your clock. So it's a few milliseconds execution, including the whole processing step, right? And now here you see also the log in my Kafka Streams application. In this case it's running in the IDE, but in the same way it could run anywhere, as I said, Docker, cloud, wherever you want to run that and scale it up and down. It's just a small lightweight Java application, but it scales well and has all the features like failover, high volume throughput, and all these things. So I'm just doing 1 second example, again, 1 line of code or 1 line of test data. The point here is just to show you, besides the prediction, yes, the flight is probably delayed, another one with no. And so you see the 2 different options, and under the hood, the model uses that. Of course, you can also build more powerful models which predict you with a specific probability. For example, let's say, yes, this flight is probably delayed with 80% or so, or maybe it is delayed for 1 hour or 2 hours or whatever, right? So this is just, again, more or less the hello world example of what I want to show here. And with that, let's go back to the presentation. So this was 1 example about how to deploy an analytic model with Kafka Streams. By the way, I also have all the examples on GitHub, so you can take a deeper look at that if you're interested. So I've built different examples with Kafka and Kafka Streams using TensorFlow, H2O, and deep learning for J. But in the end, if you tried it out, the concept is always the same. You build a model and you run it inside your Kafka Streams application. So it's pretty easy and straightforward. If you can write Java code or so, then it's done in a few minutes, more or less. The key challenge is more or less the data scientist has to process the data the right way and build the model. And you have to have the same pipeline for the real-time events to process data for the same format. So the other part was KSQL, as I mentioned. So Kafka Streams is the part for the programming language, where you write Java code for the stream processing on Kafka. With KSQL, you can do the same with SQL queries. And this is not just a request response where you get information, it's really a query which you deploy to runtime. And that scales the same way like Kafka Streams, because it is Kafka Streams under the hood. It's built for high volume throughput and for 24/7 mission critical deployments with fast performance. And in this example, what I have done, I have built a user-defined function. So typical function for KSQL are, I don't know, summarize or aggregate or filter or whatever. And I have built an anomaly detection user-defined function. Under the hood, this is Java code again. It's 1 Java class, which I have to implement once. In that, I applied an analytic model. Same story like for Kafka Streams. I embed a jar or Java class or whatever. In this case, I built an autoencoder with TensorFlow for doing anomaly detection, and then I deployed it. And here you see the workflow of that. Here you have incoming health check sensor events in real time continuously from thousands of people in a hospital, for example. And every one is applied in real time to do predictions on top of that, to see anomalies. And if there is a problem with that, that's not good. And therefore, we have all data sending to an Elasticsearch and Grafana, where you have some kind of real-time dashboarding for all data. But then, of course, if there is an anomaly where probably you will get a heart attack in the next 60 minutes, then you also send an alert to the doctor in another system. So it's just another output, right, of the Kafka topic. And that's just one example of how you can also apply machine learning to KSQL the same way like you can do it for Kafka Streams. And with that, you can do so powerful things in an easy way, because you always just have to write a little bit of Java code. But under the hood, leverage all the features of Kafka for that. And as everybody uses Kafka anyway for data ingestion, so I recommend try it out for that too. One last point here, very important. So I said in the beginning, everybody has to do stream processing, because typically for the real world processes, you have to continuously process data, right? So you don't store it to a database and you don't do request response because it's not fast enough, and it's definitely not for a large and extreme scale. But the point is, in the real world today, I'm not sure if it's a good thing or not, but the point is that typically still data scientists build a model and deploys it in a server. That's what all the tools support, like SAS or also the open source ones, or Google with TensorFlow, some kind of server where you deploy your model. And that's still possible. I mean, you can also do within a Kafka Streams application a request response call, right? That's also possible. That's a synchronous call in the stream process. It takes maybe a second, it takes longer, so you have to configure different timeouts. So that works. So it has trade-offs, and that's the most important thing to understand. So it's simple, it's easy to understand because we do request response for all the time, and it's very easy to deploy a model on TensorFlow serving or somewhere else. But you also then have, of course, the coupling to that. And if you want to do especially large scale or mission critical things in real time, anything like a HTTP call is not a good thing, because you cannot scale that and it does not perform well. So you simply have to be aware of that. And also, if you want to really leverage all the Kafka features, like exactly once processing, which is possible in the meantime, it's only possible if it works in Kafka. But if you do a HTTP request to something like TensorFlow serving, and if this request fails, then you have to handle that in your application, because Kafka cannot do magic, right? So you have to be aware of all these disadvantages. But it's a fine approach, it's easier, and for some things it's fine enough. Extreme scale is not always needed, but it's not a recommendation or best practice. So with that as last part, I'm also almost over time. So automation and DevOps, that's also very important because, as I said, there is different systems which you integrate with, and there is different models you build, and you have to automate that, especially again at scale. And the main question typically people ask then or think about first is, how do you deploy a model once and then improve it continuously? Right? So that's the main goal and that's the vision. That's what some people talk about, but that's also the hard part, and there's reasons for that. This is typically called online model training, where you deploy a model once and then continuously improve it. The main problem with that is not many models allow that today, because it's simply not that easy to build something like this, because typically you have what's called supervised models, where you have to find out if it is fraud or not, and then later you can improve it based on that. And if you don't know if it's fraud, how do you want to do that? So there's different options for that. What we mostly see is the second part is the continuous batch updating. Right? Here, you train models continuously, and you do a deployment every week, every day, every hour, whatever is good for your use case. So that's the real world what we see mostly. So you deploy your model, and then you do on new data, train a new model, an improved model, and deploy that then. And then under the hood, you use technology like Kubernetes, for example, for deploying both the Kafka parts as server side, but also the client side. That's just one of the trends we see a lot. So for that, we also build a Kubernetes operator, for example, to automate all of that. But that's then the details, and also the monitoring part. There is not really a standard for that. That's based on your infrastructure, but you have to build a monitoring system for all your Kafka part or all your machine learning part. And that's also the important thing here at the end. So let's conclude this here. Key takeaways from the session. First one, data scientists and developers have to work together continuously, both from a technology perspective, which frameworks to use, how to deploy them in production, but also from an organizational perspective. Talk to each other all the time. That's our lesson learned number one from the projects we see which failed at companies. Mission-critical scalable production infrastructure is key for success in machine learning. We have seen that in this talk, not just for data ingestion, but for deployment, for monitoring, for retraining, A/B testing, all these things. You have to think from the beginning how to do it at scale in a mission-critical system. If you just develop Python code and cannot deploy it afterwards, it doesn't help and solve any problem. And so, as you have seen here, many people use the Kafka ecosystem, not just the tech giants, but from them you can read a lot in their blog posts. But in the meantime, we see the same infrastructure built at banks, telcos, insurance companies, or retailers also, for all the different components like ingestion or processing or inference and monitoring. So with that, I think I'm already over time, so we will do questions afterwards. Thanks a lot for coming, and if you have questions later, you can either come to me or also connect on LinkedIn or via Twitter or so. Thanks a lot.